Alright, so let's take a quick look at the schematic that I have here, and I'll post it down in the links below so you can check it out for yourself. What I have here is, this is the MCU. I couldn't find the appropriate part, so I just put a generic header, but yeah, this is the MCU. I have here the 3 push buttons pulled up by 3.3K resistors, the LEDs, which, this is the pulse decrement, pulse increment to change the pulse length, and the launch. And these are the appropriate LEDs that light up when I press the buttons. Here what I have are the light gates. You can see the resistor, diode, resistor, phototransistor, and the way these work is that this is one. You can see this is one, and this is another. This works that the diode is always on, and when there's nothing to block the path, it turns the phototransistor on, which pulls the output, which goes to the MCU by the way. It pulls it down to ground, and when there's something blocking the path, the transistor is completely off, and you can imagine this voltage divider here, which pulls the output high. So I use these to measure the velocity of the projectile. Then this is the output of the trigger pulse, which goes through 1K to an optocoupler. And the reason I have an optocoupler here is because this is the high voltage path basically here. And if you don't couple this some sort of way like this, then if you have a component malfunction and the transistor short or something, you'll pull your whole microcontroller up to those high voltages that you're using, which will basically burn everything. So I definitely suggest using an optocoupler. And what I have here is this is basically a transistor which allows me to use the appropriate voltage levels to drive the MOSFET, because the issue here is that the MOSFET, if you look at the data sheet, it doesn't properly turn on up to, until about, I don't know, 8 volts or something for my MOSFET. So and the problem is that you can't, get the 8 volts from the microcontroller or whatever the VCC that I'm using for my microcontroller. So I hooked it up to the high voltage. And what this transistor does is it raises the base from ground to that high voltage. And one trap here is that you have to. There's a limitation of the maximum voltage between the gate and the drain that you can have in the MOSFET. In my case, it's about 20 volts. So I've limited it using a resistor and a 12-volt Zener. So when this transistor pulls this point up to those 90 volts or whatever I'm using, that the gate only stays at about 12 volts, which is very important. Okay, so let's look at the switching path, which is here, which you have the coil, the MOSFET, and the caps powering it. So this is the switching path. This is actually the coil that shoots the projectile out. So there are a few important things to consider here. Choosing the MOSFET, you have to first calculate what voltage you're going to be charging your caps up, and there's one parameter of the MOSFET which is called I think the VDSS, which is basically the maximum voltage between the drain and the source. Yeah. So in my case, this is 200 volts here. Okay, and I only charge my caps up to 90 volts, so that's fine. Another parameter of the MOSFET that you should consider is the RDS on, which is basically the resistance of the MOSFET, the resistance at maximum, when it's fully turned on. And in this case, you can get really low ones. This one that I have is 40 milliohms, which is the IRF R260N, which is the MOSFET that I'm using. And another thing to consider, the third thing, most important, is the peak current that your MOSFET can take. And you will, I'll talk about this in a bit, but basically you'll have to do calculations and see what current your MOSFET can take. Okay, so in my case, after doing the calculations, I see that the peak current in my circuit is about 60 amps when I trigger the circuit. And my MOSFET's rated for about 250 amps, so that's completely fine. Also, I do not suggest you push the components, especially the MOSFET, to their rated limits. You have at least 50% headroom. So if you're using 100 volts, if you're charging your caps to 100 volts, have a MOSFET that can take at least 200 volts. If you push them to their limits, you're gonna have a lot of dead components, which I had. And one last thing to consider here is the switch resistance path. So everything here is going to have a series resistance. Okay, if you have a low resistance MOSFET, okay, you can neglect that. but the coil is not. You cannot neglect that because it's going to have a significant amount of resistance. In my case, my coil is 1 ohm, okay? And I have I breadboarded it, so you can imagine the rest of the resistance, the wire, the breadboard, and MOSFET, the whatever, everything put together. And I've calculated, I actually measured on the oscilloscope. I have a peak current of about 60 amps going through this circuit when I trigger it. So you should definitely calculate or measure the current before you choose your MOSFET, etc. So let's look. Oh, sorry. Let's look at the last thing here, which is basically the voltage multiplication. What I have here is 1 op amp. It's not an LM358, it's another op amp, I just couldn't find the part. So here, what you see here is a relaxation oscillator. It's very simple, you can find it online, or you can simulate to see how it works. Okay, I'm not going to go into that. Basically, it generates a square wave, in my case a few tens of kilohertz, and I feed it into a buffer, which is the same op amp, it's a dual op amp. And from here I feed it into this TDA 2030. It's basically an audio amplifier, and I just use it as a simple op amp buffer, okay? This is just, I use this to power up, buffer this, the signal to charge the voltage multiplier. And just a word of advice, be sure to put a few caps between the power supply of this very close to this TDA 2030. If you don't, it's going to oscillate like crazy and you're not going to know why. So here you can see I've got protection diodes in the output. I do heavily suggest that you put them or sort of isolate this part, you know, the amplification from the voltage multiplier, because if you don't, again, you'll see for yourself that you'll be burning components. I also have a 20 volt and an 18 volt MOV across here, just in case something happens. And this is a Cockcroft voltage multiplier. You can Google it online to see how it works. It's pretty simple, and it's in stages. You see, you have one stage here, you have the same stage repeating. So basically, you put an AC voltage in the input, and it multiplies that voltage. Well, if in my case, I actually have this powered by a dual supply, plus minus 9 volts. So I output about a 14 volt peak to peak, sort of a square wave, 15 volt. So basically, what happens, every stage adds 15 volts. I have I'm not sure how many stages I have. Whatever it's say 10 stages, so 15 times 10, 150 volts, and you can tap the voltages from each stage depending on how high you want it. So just a few things about the voltage multiplier. Be sure that you have a high enough frequency. I once again read up on how to properly make the voltage multiplier, but the most important thing is a decent amount of capacitance. Here I have 400 nanofarads, a decent amount of frequency, so a few tens of kilohertz. A bit the smaller your capacitance is, the higher frequency you'd want to go. And so you can even do it without having this amplifier, but you need to power the voltage multiplier directly with the op amp, and it'll charge really slow because the op amp can't really provide high enough current. So I think that's about everything about the schematic.